Okay, the whole point of homework number 2 with regards to limits is actually just being able to graph these. So we're going to graph them and then we're going to have to find these limits. So there's nothing new other than we just want to review like how would I graph these. So the first one's a piecewise function, and for the piecewise function we're going to look at x to the third. Okay, so when x is less than 2, we're going to take x to the third, and if you remember how to do shifting, this is just going to be minus 5. That means down 5. So we're going to take this x to the third function and we're going to move it down 5. Okay, there, we moved it down 5. And if you look at the answer on the right, we're going to look at a few key points. Okay, one of the key points, it used to be 0, 0, but we went down 5. So it's going to be negative 5, 0. Another key point used to be 1, 1, but we went down 5. So it's going to be 1, negative 4. Okay, another key point used to be negative 1, negative 1, but now that point went down 5. So it's negative 1, negative 6. Okay, and now you know that we're only supposed to graph this function when x is less than 2. So we're going to have to remove all the rest of this stuff here. Since 2 is an endpoint, we're going to have to plug in a point. The other thing we're trying to graph is x plus 4 when x is greater than or equal to 2. Okay, I just drew the line y equals x plus 4. And we only want to graph this when x is greater than or equal to 2. So we're only going to graph this part of it. Again, x equals 2 is an endpoint, so we want to plot a point at x equals 2 for that line. Okay, this point is going to be filled in because it says x is greater than or equal to 2. Okay, on the right side, we're going to want to put arrows because the line keeps going to the right. On the left side, we're also going to put arrows because the graph actually continues on forever to the left. And now we're done. That's how you would graph this function. Okay, here's another piecewise function example. First thing I'm going to do is I'm going to look at the easy one, and that's when x is equal to 3. That's just one spot. When x is 3, it's going to be this function over here, x minus 4. So really, that's kind of like just a point. If x was 3 and you plug in your 3, you would get 3 minus 4, so you would get negative 1. So when x is 3, you're getting negative 1. So that's a point, 3, negative 1. And that's this point right here. Okay, I had this point ready. I'm going to go ahead and plug it in over here. Okay, how about when x is not 3? What does that mean when x is not 3? Well, that means everywhere else. So everywhere else, it's going to be the function x minus 2 to the power of 3. So what we're going to do is we're going to start with x to the third. Because the x minus 2 is just a right shift, so we're going to shift it right 2. So we're going to start with x to the third and just shift it right 2. Okay, so I need to move the function right 2. Okay, there we go. It's been moved right 2. Now we'll plot some easy points. Okay, one of the easy points is going to be 2, 0. Another easy point is going to be 1, negative 1. Another easy point is going to be 3, 1. And the rest of the points are kind of off of the paper. Now remember, when x is 3, it's something else. So what I need to do is, for the graph of my x to the third function, I need to put a hole at that spot. There we go. So now when x is 3, you get negative 1. Again, I would probably put arrows on my x to the third function. Okay, there we go. And there's our graph. Okay, next we're going to review how to graph a rational function. So a rational function is a ratio of polynomials. So polynomial, if you remember, is just powers of x that are natural numbers. Now this one's already factored for us, so that makes it really nice. And it looks pretty crazy because I put a lot of stuff in here. Well, let's look at the easy stuff first. This is pretty easy. What that is that's going to be a hole when x is equal to -4. And that'll be the very last thing you do. After you've graphed everything, you'll notice right here, we put a hole in our function when x is equal to -4. So we can kind of ignore that until the very last step. Now, one of the first things I want to do is I want to put the asymptotes. So the vertical asymptote is whatever is going to make the bottom 0. Okay, now the yellow part we're going to ignore, that canceled, so that's going to be a hole. But the x minus 2 didn't cancel, so that's going to be a vertical asymptote. It'll be at the x value that makes that piece 0. So it'll be at x equals 2. So if you look at x equals 2, we have a vertical asymptote. It's the blue dotted line. We also have one at -9, because -9 would make the bottom piece 0. So we have 2 vertical asymptotes. The next thing I want to look at is the horizontal asymptote. Okay, for a horizontal asymptote, you have to look at the biggest powers of x. So we kind of have to think, all right, if I multiply this out, what is the biggest piece in front? What would be the biggest piece? And the same thing for the bottom. What would be the biggest piece if I multiplied everything out? Now you don't actually have to multiply everything out because all we really care about are the biggest pieces, the leading coefficient of the biggest pieces. So if I multiply out the top, I would have x to the 4th, but with a 3 in front of it. On the bottom, if I multiplied everything out, I would have 1x to the 4th. And if you did the limit as x goes to infinity or the limit as x goes to -infinity of this piece, you would get 3. And that's because they have the same power, right? All we're looking at is the biggest power on the top and the bottom. And since they're the same, then all we care about are the leading coefficients. So you get 3 over 1. And so that's going to be our horizontal asymptote, 3 over 1. So if the powers are the same, if the biggest powers are the same, then you just take the leading coefficient. Just to review, if the bottom had a bigger power, then it would be y equals 0. That would be your horizontal asymptote. So let's look at what that would look like. So if it was like this, you can see x to the 5th on the bottom is bigger. If it was that case, you get y equals 0 for your horizontal asymptote. If it was like this, then you would have no horizontal asymptote. However, you would have a slant asymptote, and that's because the degree on the top is exactly 1 bigger than the degree on the bottom. In that case, you'd have to do long division. You would ignore the remainder, but whatever you get for your answer when you do long division is your slant asymptote. Okay, that was a review of all 3 cases, but remember what we have is the same power. We have x to the 4th on top, x to the 4th on the bottom. So we would take the leading coefficients, and that would be your horizontal asymptote. So y equals 3 is our horizontal asymptote. So that's that green line right there. Now let's talk about intercepts, x-intercepts and y-intercepts. The x-intercepts is going to be whatever makes the top 0. Remember, after you cancel, this was the hole. So we're just looking at this piece, and we're looking at this piece. So -7 and 5. Those are going to be your x-intercepts. To get the y-intercept, we have to plug in a 0 for x. If you plug in x equals 0, this is what you would get. You can see that the 4's will cancel. And you can actually cancel the 3 with the 81. You'd be left with 27. So that's kind of a tough one. The top, if you multiply it out, gives you 175. The bottom gives you -54. And you can see with a calculator that that's approximately -3.2. So we just go ahead and estimate -3.2, and we'll put a point right there for the y-axis. So when we plot our point for the y-intercept, we can just estimate -3.2, and that's going to be somewhere around here. Okay, so we have our 2 vertical asymptotes, we have our horizontal asymptote, we have our x-intercepts and our y-intercept. We're going to do the whole last, so that part will be done last. So let's pretend we don't have that yet. So let's look real quick. If we had this x-intercept and this x-intercept, and we had this y-intercept, I think we would have enough to start drawing. Now we do have to look at the power of this x-intercept to find out if we're going to cross through it or if we're going to touch it and turn around. If it's an odd power, we're just going to cross through it. So we know this is the y-intercept, and I would most likely just go straight towards the x-intercept. Because it's an odd power, it's a power of 1, that means I'm going to cross through it. So I would probably just go up. Now I can't go up over here and cross through because I know there's no x-intercept over there. There's only 2 x-intercepts, and that's not one of them. So that's how I know that I'm supposed to go down and approach the asymptote. On the left side, when I go up, I also approach the asymptote. Now, the only way to correctly draw this with a little bump in it is if you just plot a bunch of points. The more points you plot, the more accurate it is. Now, if you draw it without the bump, that's okay. Again, it's just a sketch. Now, there is some graph over here, and there is a graph over here as well. So we have to draw that part. And here's how we draw that part. For the asymptote that's associated with -9, we have to look at this. X plus 9 squared. Because it's squared, we're going to see the same things on both sides of the asymptote. So you'll notice that it went up on the right, so ours is going to have to go up on the left. If that was an odd power, then one would go up and then the other one would go down, but that's not what we have. Now, what do we do over here? Well, because there's a horizontal asymptote, we're going to approach the horizontal asymptote. Now, you'll notice that the actual graph is a little bit higher. Again, if you're looking to get it drawn perfectly, then just plot some points. But we're just doing a sketch, so my graph that I drew with my pin is perfectly fine. Now for the graph on this side, what I want to do is I want to look at the vertical asymptote associated with 2. You'll notice it's an odd power. An odd power means if one side goes down, like this one, then the other side is going to have to go up. So we should draw this one going up on this side. And then I have to find out what happens at the x-intercept. Do I go through it? Or do I touch it and turn around? So we have to look at the factor that's associated with that x-intercept. And you'll notice that it's squared. So when it's squared, that kind of means like the same thing on both sides. The left side is above the x-axis. So the same thing for the right side. It's going to have to be above the x-axis. So what happens is it actually touches that x-intercept and turns around. So when I draw this, I'm going to touch and turn around. Now I'm going to erase this because I actually want it to be one smooth curve, a nice drawing. So I'm going to erase that, try to draw it better. Something like this. Always want to put arrows. Now what do I do over here? Again, there's a horizontal asymptote. You're going to want to approach the horizontal asymptote. Don't forget, the very last thing we were supposed to do is put a hole in our function. So in order to put a hole in my function, I'm going to come over here. I'm going to kind of erase it a little bit. And to show that there's a hole in the function, I'm just going to put a little circle right here. Again, I want you to notice that the real function actually dips down a little bit like that. So if you wanted to be really, really accurate, you could plot more points and then your graph would look exactly like the real answer. So what does the real answer look like? Well, that's what it really looks like. Remember, ours did something like this. It did something like this. And then it did something like this. So ours wasn't exactly perfect. But again, it's just a sketch. We're just trying to draw a sketch. So that's how you would graph this rational function. Okay, last one. I wanted to show you this example because this is kind of weird. Most of you have probably never seen something like this. And I'm going to highlight the part that I'm talking about. Okay, for those pieces, you'll see that the top is always positive, no matter what, but the bottom can be negative. Now, whatever's inside is always going to be the same number, no matter what. So if the x was 10, you get 14 on the top and 14 on the bottom. If the number was negative 10, you get negative 6 on the top and negative 6 on the bottom. But on the top, you'd have to apply the absolute value, which would make it into a positive. So it's always going to be the same exact number. It's just that the top is always positive, but the bottom could be negative. So basically, the number itself will always cancel. The only thing that'll be left sometimes is a negative Now for this part of it, that's just 1 over x, but the x minus 2 makes it move right 2. So we end up with this vertical asymptote at x equals 2. Now if you remember, the reciprocal function 1 over x looks like this. So all we're doing is because of the x minus 2, we're going to go right 2. So we're basically just shifting it right 2. Now we have to take a look at this. We want to find out what's happening to the left and to the right of negative 4. We know if we plug in negative 4, you get 0 over 0, which is undefined. So when x is negative 4, it's just going to be an open circle. It's not, the function will not be defined. But what happens at negative 3? At negative 3, that's to the right of it, you just get 1 over 1. So that's just positive. So nothing crazy is happening there. You can try also negative 2 if you want. You get 1 over 1. You can try any number to the right of negative 4, and you get a positive 1. It would cancel to a positive 1. How about negative 5? If I plug in negative 5, I'm going to get absolute value of negative 1 over negative 1, and that'll reduce to 1 over negative 1. So basically, I'm getting negative 1. I'm getting an extra negative. So when I'm on the left of negative 4, I'm getting an extra negative. So when you put an extra negative in front of something, it will change the negative number that it was into a positive. So basically, it's jumping across the x-axis. You can plug in any of these numbers and just see what you get. You're going to see you're going to get a positive number. So that's the weird thing that this does. You can see that you're getting the exact same number inside, but because the top has an absolute value and the bottom doesn't, when you get a negative inside, the top changes it back to positive, but the bottom doesn't. So you end up with an extra negative. And so really what it does, it reflects it across the x-axis. That's a really weird thing, and I don't think most of you have seen that before. So at this spot, it's going to jump across the x-axis. That's what it does. Now you always want to plug a couple points in just to make sure that it's correct. Okay, because how do we know that it doesn't do this? It could be this here, could be this here, and maybe it jumps right here. How do we know how it jumps? So a lot of times it's nice just plug in a point, make sure it works. For example, when I plug in a 0, I'm going to get this. When I plug in a 0, you can see that the 4's cancel. And I'm just left with 1 over negative 2. So that's negative 1/2. And that's this point right here. So it's always nice to plug in a 1 or 2 points just to make sure that it works correctly. Okay, so basically, if just as a review, this was 1 over x. Because of this, we went right 2. So our vertical asymptote was at x equals 2. Now you don't see it, but there's actually a horizontal asymptote. It's the x-axis, so that'd be y equals 0. Now the weird thing about this problem was this. We know if we plug in negative 4, you get 0 over 0. That's undefined. So if we want to draw it correctly, we really want to put an open circle here and an open circle here at negative 4. And what that means is when x is negative 4, we don't have a point there. It's undefined, so there shouldn't be a point that's filled in. There should be an open circle at that spot. Also, I always talk about how we should have arrows on the end because the graph continues on forever in those directions. And that's how you would graph this really weird one. Okay, a couple examples of factoring. This is x squared minus 5 squared. So difference of squares says that this would factor into x plus 5 and x minus 5. Okay, so that's a review from like Algebra 1 or Math 1 or some of those really easy courses that we took in the very beginning. This is similar. This is 5 squared minus x squared. So you can do 5 plus x and 5 minus x. Sometimes we want to make it look like this one. So you can move the x and the 5. That's the commutative property of addition. For this one, you'd have to take a negative out. I'll put it in the front. And then that would give you x minus 5. So they do look the same, but you have to take a negative out. So this second one has an extra negative in there. The last one is just a basic example of factoring. We want to know, what do you multiply to get 28, but add to get 3, basically. Okay, the numbers that would work would be 7 and 4. Because the 3 here is negative, we want to put the negative on the 7, positive on the 4. So we have negative 7 times 4. That's how you get the negative 28. But then negative 7 plus 4 gives you the middle, gives you the negative 3.